Recording in progress. Recording stopped. Recording in progress.
Yeah. I don't know how you can do that. Yeah, I really figured it out. Yeah, like it never happened. Did you take the derivative of the heavy set? Like that?
I didn't think that. So yeah.
So I get to
Yeah, so I didn't think that. I was kind of.
There is always.
Those are advanced. And these are funny.
No, it's way weak.
we would have been.
Okay. Well, they misread it. I didn't put that on there.
Oh, sure.
Take a look at it. Yeah.
Yeah, I guess.
Very good. Well, I think we'll get started. It's nice to see all of you here. It's my honor to introduce Meredith Kupinski here, to be here as part of our colloquium series. So Meredith is not a stranger to Rochester. It turns out she did her undergraduate work just down the road. In fact, is there anybody from RIT here? There must be. Yes. Yes. So RIT is represented. I should also add in passing, for those of you that didn't know, that the newly appointed director for the Center for Imaging Science at RIT is Susan Newalter, a former professor here at the Institute of Optics and also an alum of the Institute of Optics. So Meredith didn't stick around Rochester. She went down to a slightly warmer climate and did her MS and PhD in what is now the College of Optics in Tucson. Now it's the James Wyant College of Optics. She got her PhD there and stayed on there. She joined the faculty and has been working since 2008 on a variety of different really interesting problems in polarization and polarization measurement, but also applied problems that reach into hard problems in medical optics. For example, she was able to take a sabbatical honorary position at the Polytechnic, the other Institute of Optics over in France, to work on mular matrix polarimetry for cervical cancer detection. So she's looked at polarization in medical optics, but also polarization applied to some of the really sticky problems with trying to measure what's out there in the atmosphere. So looking forward to her talk today. Meredith, welcome. Oh, we also have something for you. A little bit of Institute of Optics swag, designed by some of our students.
Looks great.
It's light work, so
Don't take ourselves too serious around here, right?
That's right. And the 90th anniversary of our jewel in the crown.
Really nice. Tom, thank you so much for the introduction and the invitation. Thank you to the Colloquium Committee for making my trip today possible. I've just had an excellent day. And to be back here in Rochester brings back so many memories. It really is phenomenal and wonderful to just take this moment to pause and reflect and remember my time at RIT. It's a great opportunity here in front of everyone to say to the department head of Imaging and Photographic Technologies, Andrew David Hazy, who's there in the back row. Hey, Andy, look at me now. And thank you for this marvelous department and for the wonderful education that RIT gave me. Opened up such a world of possibilities. So today I'm going to talk about polarization observations from cloud emission to Fresnel dominated scattering. This is a picture of our building in Tucson, Arizona. This is a polarization picture that I took about 10 years ago when I started in the field. And so you can kind of make out like the different colors on the windows. For those of you who have been to see the building, so what we're looking at is the offices that have glass floor to ceiling to face the beautiful mountains to the north. And this building was completed in 2007 and everybody's very excited about it. And I don't know, maybe 5 years later, these windows start spontaneously cracking. Even once it happened when someone was sitting in their office, right? And so, you know, we know as optical engineers, right, this is the stress induced in the annealing process of the glass and of the mounting. And so we went out with the polarization camera, and Russell Chipman and I said, let's see if we can predict which is going to be the next window to pop. And then we said, no, too much liability. We don't want to do that. So this is us. I just graduated my first 2 PhD students in May. It was such a happy semester. And Dr. Shanks is now at JPL as an optical engineer, and Dr. Omer is at Meta. And their work will feature prominently in what I talk about today, as well as all of the other students. We always have an undergraduate research assistant with us. And so all of the work, of course, that I'll talk about today, I'll bring back to the students. Do you guys know that cactus are very polarizing? Do you know it's very hard to Google polarization and find anything other than political information? So I say cactus are polarizing because whether you think optics should be done in Rochester and Arizona really divides us, doesn't it? You know? So I did this for our winter school. These are just my warm-up slides. And so I'm just taking the little plastic sheet polarizer and rotating it, right? And so you see, of course, the cactus does not change. It's not very polarizing. If I built the polarimeter, we might actually see a few % magnitude of polarized light scattering coming off the cactus. But, you know, at this kind of precision, we're not going to see it. But you do see the sky modulate, right? And so most of us learn that Rayleigh scattering of the blue sky is in fact quite polarizing. So this is just another one where you can ask yourself what's going to disappear now when she rotates the polarizer. And it's those first surface reflections off of the pool, right? But you can see other features underneath the pool, looking at the steps, looking at the side of the walls that don't necessarily modulate. But there is a orientation of this filter, right, where I can completely extinguish those first surface reflections, but not like the shadow of the umbrella, right, that's projected on. So when you think about polarization, you really start thinking about the light paths, right? It really gives you a lot of clues as to what is the dominant process, right? And what path is the light taking? The polarization tells you quite a lot about. So here's the speedometer that's projected in my car, right? So this is down on the front panel and then reflecting off the windshield to the driver. It's a terrible design in a way, right? That it's so linearly polarized, because for me, when I put on my polarized sunglasses, I see one smile and nod too, right? I can't see the speed. So if you see me driving in Tucson and I start wondering if I'm going too slow, I have to do this, right? To check out my speed. Right, but of course, this is the Fresnel reflections, and we learn these equations, and we start to expect, right, that this light at a very grazing angle off of this glass is going to be quite polarized. And so visualizing polarization, right, is always something in all fields. How do we visualize our data? How do we explain our data? Not so necessarily obvious. So here I'm showing you the angle of polarization of the sky around the sun. And so the middle of the picture where the sun is just all blown out. And then the false color is to show you the orientation of the polarization. And so instead of putting it on a color bar, I'm going to put it on a color circle so that you can kind of start taking the colors and associating them with an orientation. And I put the black double arrow bars on there too. But the point is, you have the expectation that the orientation of polarization is going to follow tangentially around the sun. Right. So if you look up at the sky, at any one patch of sky, what will be the orientation of polarization? Well, it depends on the time of day, right? On the sun's location in the sky. And that kind of information is what makes understanding radiative processes in the atmosphere, polarization can be a really important part of. And so the Earth's radiation budget is trying to quantify, as radiation is coming to the Earth, what are the different heating and cooling processes that are going to occur? And so clouds, as you can imagine, are a really big part of this Earth system's picture, right? There's all kinds of atmospheric transmission that's spectrally dependent, right? You can have clouds that have a cooling effect because they bounce radiation back to space. You can also have clouds that have a warming effect because they act sort of like a blanket, right? Keeping radiation into the Earth. And so for these types of Earth systems problems and radiative transfer modeling, polarization is really important. And it must be both angularly resolved. We need it at many different scattering geometries, and spectrally resolved to help this inverse problem in radiative transfer. And what we want to know is the microphysical properties of the cloud. What is the size? What is the shape distributions? What is the speciation? How did the cloud nucleate? What's the thermodynamic phase? Is it a water cloud? Is it an ice cloud? If it's an ice cloud, what are the structures of the ice crystals? Because all of these will have consequences for the radiative properties of that cloud, and therefore the radiation budget of the Earth. So NASA uses technology readiness level, or TRL. And so in visible wavelengths, the TRL for polarimetry, well, it's maximum, it's 10. There are satellites right now measuring polarization in visible wavelengths. And there'll be more coming online very soon. So Maya is one out of JPL that Russell Chipman and I, especially Russell, have worked on for many years. And Dave Diner is PI of that instrument. And so in the visible polarimetry and its use to atmospheric sciences is very well established. What I'm going to be talking about today is thermal polarimetry, looking at long wave radiation. And there you can imagine the picture is a little bit different, right? The clouds can be absorbing, they can be re-radiating. So these kind of paths that the light can take, that the radiation can take, are different when you move into thermal from visible. But it can still serve the same problem of Earth's radiation budget, because we want to start looking at very thin optical depth ice clouds and answering those same questions about what are the microphysical properties. So when you look at these climate models, right, there's disagreement among instruments, disagreement amongst modalities. And one of the things that's kind of tuning parameter or fudge factor is how much thin cloud cover there is, the very wispy little cirrus clouds, the altitude of those, the thermodynamic phase of those. This is considered to be a large part of the uncertainty in the Earth's radiation budget. And there's instruments such as the IceCube project at gigahertz. So this is like submillimeter and microwave bands that's looking at estimating ice water path of clouds. Now, where thermal polarimetry comes into play, and these are both simulated results to kind of motivate our instrument development. But on the left here, this is showing long wave IR sensitivity using a split window approach. So measuring both in the submillimeter and polarimetry in thermal. And here, higher sensitivity is better. And so what we're really after with thermal polarimetry is very low optical depth, wispy kind of cirrus ice clouds. And we'd like to estimate things like ice water path and the shape, the structure of the ice crystals. Now, we're not there yet. The project is about developing the instrument and making some of the first high altitude observations, but this is our science motivation. And I should say also the signal is very small. We'll talk about brightness temperature a little bit. These are the units of thermal radiation. But here on the right, the simulation is just showing what would be the brightness temperature holding a horizontal polarizer. And then if you subtract from that, the difference with the brightness temperature holding a vertical polarizer. So much like the little warm-up slides I had, right? And what you can see is under a Kelvin for this particular scattering geometry. So a very small signal that we're hunting, of course. So our instrument we lovingly call the IRCSP, and this was designed by Dr. Shanks in her first semester as a PhD student. You see it here on the left in its first form being fabricated. On the right, there it is mounted up. I was telling the students when we go on this high altitude balloon, you get so excited to put your instrument at 30 kilometers. And I just could hardly believe it the first time they said, yeah, just mount it on a piece of plywood and drive it over to us in New Mexico, platter it up. But there it is ready to go up on the balloon. Our first flight was the summer of 2021. It was a nice cloudy day. So there it is going up in the balloon and Kira's first optical engineering paper. Jeremy Parkinson is a master's student in our group. He's the one making the stress object coefficient measurement problem I was telling you about. And he was also instrumental on this project. So this is a collaboration out of Goddard, and Dong Wu was the PI. He had several instruments. We were going to be using the split window approach. There was a sub-millimeter instrument as well. The CubeSat project was canceled, but we were successful in our piece of the instrument development and went out on a balloon. So we're looking here at 8 to 12 microns, and the science specs were 1 micron spectral resolution, and we had some size, weight, and power swap requirements related to CubeSat deployment. For thermal imaging is quite a big one. We'll talk about that. So I'm going to try to speed things up a bit and talk about some phenomenology, like why would something into the thermal waveband be polarized and why that could potentially be interesting at all. And then if you've never heard of channeled polarimetry, which based on chatting with the students at lunch, every time I get to be the first person to tell someone about channeled polarimetry, it makes me very excited. As an instrument concept, it's certainly nothing invented in Arizona. Again, I was working on the project a long time. I thought the seminal paper was Oka in the 90s. And then someone at U of A Astronomy showed me, oh, Nordsick in the 70s also thought of it. So it's a very clever instrument concept, and I'll try to say enough things to make you interested to want to look up more. Then I'll talk about some of the optical design and engineering challenges that we faced and show you some of our field measurements. So for thermal radiation, the units, of course, are still watts per meter squared per steradian for radiance, but we're now looking at brightness temperature. So everything I'm going to report to you is in units of brightness temperature. So just to understand the origin of this, here's at 3 different kinetic temperatures, 300 being around room temperature, and what the spectral emission of black body radiation is. So the black body radiator absorbs everything, emits anything, but there's no scattering, there's no reflection, right? So this is the emissivity of 1, and you would get curves like here at the top. In practice, the brightness temperature and the kinetic temperature are not the same because things are gray bodies. So typically the emissivity, the absorptivity is not equal to 1, and there are some reflective and scattering processes as well. So you can see here that for ice and water, the emissivity, although not 1, is very, very close to 1. This is one reason that we lived in fear of condensation on our optics during our deployments. But we'll say a little bit more about ice and water. And of course, the emissivity can be very spectrally dependent. You can see here a nice transmission window for glass, just above 8 microns. So again, when we talk about that polarization difference, and please just think of it as like a sum over difference at 2 different orientations of the polarizer. What we see is that at any boundary where we calculate a solution to Maxwell's equations and solve for those reflection and transmission coefficients that will be different for S and for P radiation. When we do that for an optically thick ice sheet, what we see here is the spectral emission and reflection, again, as a function of view angle. So when I want to, again, use polarization to invert radiative transfer, I need it at many different acquisition geometries, right? And with spectral resolution. And so immediately what we see here is this polarization difference tends towards negative or tends towards something vertically polarized for an emissive process as compared to a reflective process, a reflection process. So I think just thinking of PD and the sign of that polarization difference as giving you some indication on if you're looking at primarily emission or primarily reflection of thermal radiation. So for example, if I take a picture of a palm tree and the top gray one is just my digital units out of my thermal camera, this is again just a FLIR sensor measuring broad band. And here I'm looking at S1 and what I'm seeing is a difference with the cold sky, right? Like a cold sky background as compared to the palm tree, right? That has some kinetic temperature, it's, some body emitting, right? In these peak thermal wavelengths. And so the polarization and the the sign of the polarization is telling me quite a bit about if this is a absorptive or reflective type of process. And so when I think about long wave infrared scattering and what is in the atmosphere, we talked about Rayleigh scattering in the beginning, right? Looking at the blue light and the polarization signature. Now that I'm closer to 10 microns, I'm closer to a me scattering regime for my ice crystals. Cloud ice can be between 10 and 100 microns. And so one of the things that we're doing in the lab at the moment is thinking about an ice-water discrimination task now that we have the ability to spectrally resolve thermal polarization. So you can have ice just near its melting point. You can have a very similar kinetic temperature, but because of the difference in that emissivity, as I look at the horizontal axis for scattering angle, the vertical axis for scattering angle and the horizontal for wavelength, I can see some polarization differences in certain wave bands between that ice and water that I would not necessarily be able to resolve without polarization. So let's move on to talking about the optical design. So here was some of our flow down requirements that I'll skip right through. Those of you that are working with the uncooled microbolometers can appreciate the picture on the right with the size of just the quarter. So going into this project, part of the vision of Dong Wu, our PI, was to really want to see if we could properly calibrate and quantify, use for a scientific purpose, a microbolometer. Typically, these have a lot of lookup tables that you have to turn off because they're trying to maximize for dynamic range in a given scene, right? And so we did an awful lot of work to stabilize the readouts of these microbolometers and demonstrate them in a low pressure environment. Okay, my favorite slide. So I know there's a lot going on here, but this is how we measure polarization with no moving parts and encode it into the wavelength of light. So please imagine here, I don't think I have I think I'm just going to advance this if I touch it. I don't have my virtual laser pointer. But here coming into my collimated assembly, please imagine that between 8.5 and 12.5, I have all the same polarization state. And I'm using color for wavelength, even though I'm in a thermal wave band. It's going to pass between a quarter wave plate and the high order retarder. So the high order retarder has a birefringence that, of course, due to dispersion, is different across this wave band, right? So there's going to be a rotation of those linear states, but the rotation is going to be wavelength dependent. So what's emerging from that quarter wave plate and high order retarder is a rotation that's going to be different for each wavelength. I can then go through a linear polarizer, really anything that would split orthogonal states. It could be a Wollaston prism as well, so that I can have some way to tell what is some way to split S&P, some way to code into the intensity in these two different paths, what that polarization state is. And so what you see is going to my two diffraction gratings. I have this sinusoidal form where that carrier frequency is going to be what tells me what is the polarization state. And so you see on the bottom, some of me just running through some of this math. And so the frequency of that periodic structure is related to the spectrally dependent retardance magnitude. So as I said, when you want to convert that angle into intensity, you could use, as we did, a linear polarizer. There's a lot of engineering reasons we did that, or a Wollaston prism. And then you just need some way to do spectral analysis. So some kind of dispersive element, like either a diffraction grating or a prism, to decode or to demodulate that carrier frequency as a function of wavelength. And so you have several free parameters here, but one of them, of course, is the thickness of, in what our case is a cesium, a cad selenide crystal. And so on the top here, we're showing the refractive index. And again, the way the birefringence is a function of wavelength. But as the crystal becomes thicker and thicker, what I'm going to have is a faster and faster carrier frequency. Now, this is good in some way because then I can have better spectral resolution, right? Because I'm going to have to sample this waveform over at least one period. So with a thicker crystal, I can have better spectral resolution, but then I need an imaging system that's going to be able to resolve that carrier frequency, right? Or a spectrum analyzer that's going to be able to resolve that carrier frequency. So that's some of the design trade. And that's what this looks like. So you have working together the thickness of the high order retarder, the spectral dispersion. So the line pairs per millimeter for the grading. And then the focal length and the pixel pitch to make sure that you're adequately sampling this modulation frequency. So what do you do once you have everything designed and you think you can resolve this carrier frequency in two paths? You simply calculate the sum over difference of the two paths. And this comes out to tell you a lot about your polarimetric efficiency, right? So the bottom, the polarimetric efficiency is plotted on the bottom there. And here what you see is the efficiency does get better at the higher wavelengths, right? And this is largely due to that carrier frequency being larger at the larger wavelengths, right? And harder to resolve at the shorter wavelengths. And some people say, well, if you're going to ascribe any specular change in your data to a change in polarization, I guess this can never work unless you have a flat spectrum, right? And so this is in fact why we need the two-path solution, right? Because we are going to have a spectral transmission in the atmosphere, right? That's the graph in the top, right? So we can't assign every spectral change to polarization. But this is exactly why you need the two-path solution. You somewhat normalize that out. So what was really not just nice about our design, but required by our design is that we were able to minimize our custom parts. So the high order retarder was our most expensive by far component. And the diffraction gratings as well were custom, but everything else was done completely off the shelf for our instrument. So the contrast in the linear polarizer, this is just simply a wire grid polarizer. So it operates much more effectively in the transmission mode as compared to the reflected mode. The efficiency of the reflected path is only around 20%. What's true in polarization and in just about any other imaging system, right, is there's the things that if you can characterize and know them, right, then you can take care of in the data processing. And luckily in polarimetric calibration, this is the way it goes, right? So as long as we know it. I love when I teach the course at Arizona on inverse problems. I think it's written in my PhD advisor's book as well, Harry Barrett, you know, if you want to solve an inverse problem, please get the forward problem right? And it's never been more true than in polarization. So here's some of our calibration setup. And so if we go through and do a very narrow band polarization response, this is what we look like with our two paths. Our two paths are out of phase from one another. And as I rotate the polarizer, which is what I'm doing on the vertical axis, right? Then you can kind of see that it's the phase of this carrier frequency that's encoding that angle of polarization. So you can see that shifting as I rotate my polarizer. So that was something of a first light result, right? Every time we mess with the instrument, we always say, go check for modulation. Is the instrument okay? Go check for modulation. This is what we like to see. Again, with a fully polarized source. This is fully polarized in calibration. And so this is what our modulation function looks like. Again, the modulation being something between -1 and 1, and the magnitude being 1 being most ideal. Now what we're seeing with the from real data, not just from modeled, is that due to the quantum efficiency of the uncooled microbolometer, it's sort of falling apart at the longer wavelengths here. But seeing a good expected response up to about 11 microns. So I still remember the day Kira came into my office and was so happy and excited. We had the narrowband results with the monochromator, right? And then we're working with the black body and starting to do retrievals. And she was taking one of our image science classes and she said, we haven't considered the continuous to discrete model, right? So if every one wavelength we're activating only one discrete element on the detector, right, then the narrow band would tell us everything we need to know, right, about measuring polarization of broadband light. But instead, what Kira realized, because she was paying attention in class, is that we need to take into account the point spread function and further still, the spectrally dependent point spread function of our system. And so in this way, you can design your slit, right? Because you need to be able to have resolution. You don't want to open up that slit too much. And so in the end, this is what the modulation of the broadband illumination looks like. And some example in the two-path system. Again, polarimetric efficiency going up as a function of wavelength, just due to that carrier frequency increasing and being easier to resolve, and then coming back down again due to the quantum efficiency of the detector. So when we talk about these responsivities of the uncooled microbolometer, you really need to keep the focal plane temperature constant. And so what we're showing here is just what the digital readout looks like as you're changing the focal plane temperature, and it will sort of go in concert, right, with one another. So even though it's uncooled, what we ended up doing in our first flight, we didn't have very good thermal management, but we warmed it just a little bit, just enough so that we could keep it consistent, right? So we make sort of a sacrifice for measurement noise, right? With at least having, again, good calibration, a better forward model by keeping the focal plane temperature stabilized. So now you have the measurements. How do you demodulate, right? How do you get back to the carrier frequency and use that information to get an orientation and a magnitude for your polarization? What you have at the focal plane is not even samples in wavelength, but you have even samples in wave number. And I think when I spoke to Janique about this problem, she told me it's very similar in OCT, right? And in many fields. And it's similar in astronomy as well. And so we were lucky to, in a way, find a off-the-shelf algorithm solution, right, in this case. And the Lomb-Scargill periodogram is actually very nice because it's chi-squared statistics. So even if you have noisy data, you can set a confidence interval for a detection of a frequency on an uneven grid. And of course, interpolation, other methods work as well. But I like this because it's a statistical test. And so for the data I'm going to show you, we set a confidence interval to 98%. And so at the end, when we asked ourselves if we're meeting spec for this 1 Kelvin in polarimetric precision, here's some room temperature, again, results, and a contour here. I don't have my laser pointer. A contour here where we said, well, we're meeting 1 Kelvin over most of our wavelength of interest, at least for room temperature, slightly above room temperature targets. And we expect, of course, that precision to get better when the focal plane is colder. So I'll say a little bit. And so what I'm going to show you with channel polarimetry, you have this choice when you demodulate to define your 3 different bands. So we defined a water vapor band, an ozone band, and then a clear band. We didn't have any scanning for the purpose of our first flight, right? We're keeping things simple. So I just had a static point of view, as you can see in the CAD model. And this was the amazing monsoon in the Southwest, right? Not this past summer, but the one before. It was like rain every day. The flight was rescheduled 5 or 6 times, which actually is quite normal. And so the purpose of this video, well, it's just so fun to, see scientific high altitude ballooning. But look at all the gray cloud cover. We couldn't really have asked for like a better day to be doing this campaign. And on the left, I'm showing data from the GOES satellite so that we could monitor cloud cover. We also get brightness temperature off of the GOES satellite. And brightness temperature is linear with optical depth of the cloud, right? So we also get to know some things about the optical depth of the cloud that we're looking at. So the big takeaway when all was said and done, we did measure some degrees of linear polarization up to 20%, right? So what I'm showing on the bottom is the time course of the flight versus the magnitude, or what we call the degree of linear polarization as a percentage. You see this kind of periodic structure with our data. We have a lot of suspicion that this is related to the rotation of the gondola because the time scale here relates to what they tell us is typical for how that gondola of the balloon rotates. And here's a picture of the brightness temperature and showing here where the altitude was 5 kilometers and up to 30 kilometers. And so one of the sanity checks is looking at the radiometry and making sure that as your altitude is decreasing, your absorption to ozone, right, is decreasing your radiance. And so the fact that we see the brightness temperature in that ozone band go down as a function of altitude is something of a smell check for us. And here is how the magnitude of polarization correlates with brightness temperature. And without knowing it, when I showed this to some of our atmospheric science collaborators, they were thrilled because they see exactly this in the microwave. And so in a way, you want to be close to the science application, but well, at least I wasn't biased knowing this beforehand. So as I said, brightness temperature correlates something with optical depth. So consider at the higher brightness temperatures on this graph that we don't have any cloud cover. And so they expect mostly unpolarized radiation radiating from the Earth up from a clear sky. And as the optical depth of the cloud starts to grow, this is when you expect to have some cloud top emission. And it's emission from these clouds that's contributing a polarized signal that starts to grow as the brightness temperature is decreasing, as the optical depth of the cloud is growing. And so what about the apex? As that cloud continues to grow in optical depth, you can basically think of having emission at different altitudes, at all of these different layers that then begin to depolarize with one another. There's in fact, Ji Gong at Goddard, as well as Dong Wu, have taught me some other polarization phenomena they expect for some very high optical depth clouds, but I don't think we yet have the polarimetric precision to resolve that just yet. But this is certainly an exciting result, right? We were nice to see this correlation structure, even when we were heating our focal plane. Dr. Shanks invented, just as I showed you the way it's nice to take the angle of polarization and put it on a wheel because it's an orientation. Look how clever she is. She figured out how to do a histogram that's radial, right? And so in this way, it's nice because I think if you're measuring just noise, you're not going to have an expectation that there's any preferential orientation to the polarization, right? And although we have some uncertainty because there's going to be gondola motion that we don't necessarily know, right? There's certainly some artifacts in this data. We at least see some preferential structure when we analyze our AOLP, our angle of linear polarization. So that went so well. We were all excited to do it again. So we wanted to go up this summer, but we said, let's make it even better. So we want to do, again, we were terrified of condensation on the optics, right? Then that would be basically like putting a shutter on the camera. So we decided to heat. So this time we said, let's purge with nitrogen. This way we can cool it and not be worried about having condensation internal to the instrument. We put a lens heater on the first element. We put a context camera. I think I skipped over it earlier, but we didn't have any pointing information on the balloon. So the best we could do is say, oh, somewhere in the donut, right? So now we added a context camera. In the middle is the instrument. There's the little radiator on top. Added some sensors and telemetry, taught ourselves some things about PID controllers. And here's what happened to our instrument on the second balloon flight. And so you can see the tree branch in the left picture, right, reaching in And that's our instrument that this awful tree branch was reaching into. And luckily the electronics took a hit. The electronics got quite damaged. The optics survived. But the SD card popped right out and was damaged on impact. So, you know, when they say failure is part of success, it's true. We don't have to like it, but we have to accept it for sure. What was successful is Jacqueline John, who's just starting her second year in the PhD program and inheriting this project from Dr. Shanks, was able to take this up in a passenger aircraft that flew out of Wallops. NASA's very good with the outreach, and so they had also some students that go up on the aircraft, and Jacqueline gets to tell them about her dissertation, and this is all through the SASA program. So we got to go up on 3 different flights, and Jacqueline's in the bottom right, interacting with some of the SASA students. And there's Jacqueline, Jeremy, and Grady was an undergraduate doing an REU from Yale that was with us during the integration onto the aircraft. So we did get some data this summer, analysis forthcoming. Okay, now I'm going to switch to another project, which second year PhD student Clarissa De Leon has earned herself an NSF fellowship to pursue. She's interested in ultraviolet polarimetry for wildfire science. And so we have the ground-based instrument that you can see her working on. We can take this out to controlled burns in Arizona. One of the things that happens as smoke ages, as it propagates in the atmosphere, is that it whitens, so the albedo changes. It also kind of picks up other stuff in the atmosphere, so it becomes less spheroidal and it becomes bigger. So these are things that we can track with polarization. And then, you know, I was talking to the students, I said, in an academic research group, you never compete, you just try something different. And so someone said, can we do anything on a UAV? And I said, well, we could just stick one polarizer on a UAV and then we could drive the UAV really crazy, right? Instead of spinning the polarizer, we can spin the whole instrument and put that into radiative transfer models. Clarissa's learning how to actually do these inversions so that she can do data products, as I said, like the microphysical properties relevant for atmospheric science. So that project is just starting to get off the ground. So the other part of the group, we focus in computer graphics and computer vision. And when you look at how they model polarized light scattering, it's more or less just these 2 terms. They say, well, it's diffuse, it has some bulk scattering component, it's absorbed and interacting with the material in some appreciable matter, or it's just simply first surface reflections, right? And so we asked the question, if these models are so simple, maybe the measurements also can be. And so on the left, here's a full Mueller matrix just of a pink sphere. I think this is a billiard ball, or no, this is silicone, pink silicone sphere. I'm about to show you a lot of spheres. So this is what you do in computer vision because you have a nice sampling, right, of all of the angles and all of the out of plane scattering. And so on the left is the full Mueller matrix measurement, and on the right is what we call triply degenerate model, which reduces by a factor of 2, and you should see there's a great deal of visual agreement. So this is what our polarimeter looks like, and there it's scanning around little Kirby. I'm getting a laugh, so somebody knows Kirby. Quite a few people know Kirby. And so the schematic of the instrument is these rotating wave retarders, right? And so we're taking 40 measurements here of Kirby. Maybe it's because I'm a medical background where we're always trying to lower dose. I said, does Kirby really need all these polarization states on him? You know, like he's probably not doing it's not like ellipsometry on Kirby, right? Like what's the simplest measurement that we can possibly make? And so I hope many of you are getting a chance to interact with these commercial off-the-shelf polarization cameras, much like the Bayer pattern has the RGB filters for color. Now Sony is patterning the focal planes with polarizers at different orientations. So you can just in one snapshot in the visible measure polarization. So in the upper left, here's our sample. This is just blue Legos. And then we know that texture is going to change polarization, right? If you think about that reflection diffuse. So we just do different sandpapers to roughen them differently. And then we take a picture with the snapshot polarizer and we say, can we get can we extrapolate back to the full Mueller matrix? And polarization is nothing if not coordinate system soup. So I'm not going to pretend we got this right the first time, but this is assuming a Fresnel dominant process. And it's a lot of on-plane scattering. It's not a sphere, it's a flat sample. But on the left is where we've measured the poor patient 40 times, right, in the very expensive polarimeter. And in the right column is where we've done the commercial off the shelf, only 4 measurements, and managed to extrapolate the Mueller matrix. So that leads into our interest in physical-based rendering. This is like incoherent ray tracing for graphics applications. Most of these physically based renderings do not consider polarization, but polarization is of interest. It's considered a way to add some realism, add the twinkle in somebody's eye, get all the nice specular reflections just right. And so these PBR engines are Monte Carlo simulations, right? Just like we're familiar with in our coherent ray tracing for wavefront aberration. So we're launching rays. Knowing the way that an object radiometrically scatters light tells you which rays are most important to sample, right? So the geometry of all these rays in the picture is based on important sampling from knowing the bidirectional reflectance distribution function of the objects in the scenes. So what this kind of led us to, just gonna go a little bit faster. So here's the BRDF of the material. And if you can know that, then you can have a better way for sampling ray geometries. When you want to do this in polarization, you now need to have a polarimetric BRDF that's gonna be Mueller matrix valued. But if I can know that dominant process, like I did when I was doing the extrapolation problem, then I think I can introduce the concept of a polarimetric importance sampling that's going to help me speed up this whole calculation. So Mitsuba 2 is a very nice physically based renderer that we decided to do our initial studies in. And so here's 25 different materials that are characterized with the full Mueller matrix data set. We take that, we compress it all by a factor of 2 with our triply degenerate model. And then we render it up. So in the other time when I did the side-by-side, I had simply like truncated the measurements, right? Now these are renderings where I've actually described the material with 8 numbers instead of 16 for its polarimetric properties. And again, getting some good visual comparison. So if we think of this Mueller matrix, the specular diffuse, as like a stochastic process, right? And as the ray comes in, which one should we do? Should we consider it totally depolarizing, or should we consider it just a Fresnel interaction that allows us to break apart the problem into something coherent, fully polarized, and something that's radiometric? I think it also allows us to use a lot of the existing computational infrastructure in computer graphics and then just overlay some polarization functionality. So when we do this probabilistic implementation, we fully expect it to be the same side by side, right? So this is just something of the first reality check. And again, was the dissertation topic of Dr. Omer now at Meta. So here we render up a little scene of robots, and the top is the degree or the magnitude of linear polarization. We show on the left the original, you use 16 numbers. Our model in the middle, you use 8 numbers. And then in the final row, use our model with 8 numbers, but this idea of polarimetric importance sampling that we hope will make these computations much faster. That remains to be seen. Ongoing investigations. And here's the same thing. This scene is really tricky because if you think about the ray depth, how many interactions does it need to get from source to camera? Here, as you're in shadows and have many penumbras, right? This would be considered a very difficult scene to render. So I think the outlook in all of this, or my outlook, and I've really enjoyed the lunch with the students. I know that when I came to U of A, they said, Meredith, are you a theorist or an experimentalist? And I mean, the true answer was, I have no idea who I am, right? But I think the longer I work in optics, the more I so much appreciate, right, that having both is where you can really get into a fun play space, right? Like, can I solve these problems in the hardware domain? Can I solve them in the computational domain? And this is where I think for me, a lot of creativity presents itself. So I think we're demonstrating how to do some low-cost technology development and testing in a university environment. Again, test out some weird creative ideas. And as always, right, like thinking about commercially available technology. And now everyone in computer vision is measuring polarization because it's only $2,000, but I take it upon myself. If I'm any kind of expert in polarization, right, then let me figure out what's the most we can do with this commercially available polarimeters. That's what I'm pursuing. I love working at Arizona. That's kind of clear because I've been there over 20 years. And they just came out with a land acknowledgement statement for our local Native American tribes. There's 27 sovereign nations in Arizona. And so the campus is located on the Tohono O'odham National Homelands and the lands of the Pasquayaki tribe. Where we launch our high altitude balloon is Fort Sumner, New Mexico. It has a very sad history as part of the Navajo Nation Long Walk, part of the imprisonment camp in New Mexico. So doing research in the Southwest, working with Native American students, having an audience like this, and to acknowledge the sovereign nations of Arizona is such my great pleasure. Thank you for today so much, and thank you for attending my talk.
Thank you. We have time for some questions. So I'll start out with one. When you're dealing with those very broad bands in the infrared, what's the most challenging component in terms of the design and implementation to do polarization measurement?
Most challenging component in the infrared.
For example, I've looked at wired polarizers, and they have a spectral bandwidth associated with them.
Yes, I think definitely. We wish we could have gotten a Wollaston prism. So what we were trying to pursue originally was a one-path design, right, where we would have just had one camera come off of a Wollaston, right, and just use one focal plane. Because in our two-path solution, we use a very, very small portion of each of those focal planes. So we would have loved to have had a Wollaston prism solution. There was some discussion about a tellurium Wollaston prism, but that got very expensive very quick, and finding somebody to code it. I expected the diffraction gratings to potentially be difficult to source, but OPCO made those for us, and they performed very well.
Questions? Yes.
You mentioned like the challenge of the thing spinning around and like not knowing how it's oriented.
Yeah.
Have you like tried like some sort of gyroscope or something to help give you information or?
No, it's certainly like a possible problem to be solved. Again, like I think doing research in an academic environment, you just have to kind of like triage everything, right? Like always triage your wish list, right? They're like, there is no Santa Claus, right? You can't just like get everything you want for Christmas. But it's certainly, and then when I go to atmospheric science meetings, right, even there's telemetry, right, so that I could account for changing the gyroscope, the gondola motion, right, that's going to change my polarization information. I was working in polarization for far too long when somebody said to me, well, Meredith, what if the camera is not on the tripod the right way? You're going to get a different answer. And I was like, oh my gosh, they're right. I haven't even thought of that yet. So you want this information about your lab coordinates in a three-dimensional space. And there is telemetry to help with that. I just need to keep going.
I had some more questions about the high order retarder. What were you using it for again? Kind of lost that.
Yeah, so we'd have a quarter wave plate followed by a high order retarder. And those two elements in series make a circular retarder. And so what that means, like when I was at Professor Roland's lecture, doing guest lecture, right? I said, one of the great things about the Poincare sphere, other than it's beautiful, and my students like to pose with it in pictures, right? Is that it can tell you about the action of retarders, because all the retarders are rotations on the Poincare sphere, right? And every rotation of a sphere, weren't you the one I was talking about this, right? Has an axis of rotation, 2 points, right? And then a magnitude. And so the circular retarders, the axis of rotation is the circular states on the Poincare sphere. So all those linear states on the equator are going to be rotated. And then the amount of that rotation is what's spectrally dependent. Yeah.
I'm still confused with the spectral blurring part. So is it?
Yeah, I'd explain that so fast.
Yeah, so is the spectral blurring, I can understand that it's because the points is wavelength dependent. Is that it?
The point spread function is definitely wavelength dependent, right? And so if you think of it, if you were measuring like at wavelength 1, right, you'd have the point spread function isolated. Maybe it would take up, several different detector elements. And then at wavelength 2, it might shift, it might have a different size. But in broadband, you have them both together, right? So then you have some uncertainty there, right? Of like, it adds some uncertainty to the spectrometer.
Let's see, over here and then. Yeah.
Okay, so Professor, yeah, I'm just interested like can the polarization structure of a cloud like can reveal any information about like the macroscopic structure of the ice crystal like in that cloud or like, and also like maybe like the falling altitude of the ice crystal?
The altitude, yeah. So the altitude very much has to do with like where you're going to see ice crystal structures, right? And so I sort of know the answer to your question. I can tell you some interesting things, but I'm not like a big radiative transfer of the atmosphere expert, right? So the most ice crystals, the most ice clouds in our Earth are actually in the tropics, right? And it's so shocking. I thought, oh, let's get the instrument and go to Antarctica, right? Because in the tropics, we have particulate matter for nucleation in the upper atmosphere, right? So this is why all the ice clouds are hanging out there. And there's definitely interest for using thermal polarization. Again, it would have to be angularly resolved and spectrally resolved to figure out different ice crystal structures, right? There's many, right? Like no two snowflakes are alike kind of stuff. And so Sylvia Sullivan is a great new hire by the U of A in our chemical and environmental engineering department. And she's going to get an ice crystal growing chamber, and I'm going to figure out how to stick a polarimeter in there. So I maybe have a better answer for you later.
Meredith, you just destroyed my follow-on. I was gonna say, if you want clouds and ice, you come to Rochester. There's the tropics. Ben.
Yeah. Any spatial information, or are you just like averaging over the slit field of view from your spectrometer?
Yeah, so right now we do a little bit of averaging, and if you wanted spatial information, you would have to scan for spatial information.
Okay.
Yeah.
Is that something that you would plan for like a future instrument to have spatially resolved information as well?
Like just keep me out of the trees, and then I'll think about scanning the image. Yeah, no, it would be great. It would be great.
Why launch in New Mexico?
Why launch in Mexico?
Yeah, we're just a piggyback mission, right? So I always tell Dong Wu, our PI out of Goddard, he dreamed a bigger dream for us than we could dream for ourselves. I think part of the advantage of this project is the U of A president really allowed us to stay busy during COVID, right? A lot of this work happened during COVID when the university didn't shut down and the federal government did. So everyone at NASA was like, oh my gosh, look at all you guys are doing. And it was suggested by Dong Wu because we can go, again, at the piggyback. You have to pass like a safety review, right? To make sure nothing will fall at high altitudes and stuff like that. But yeah, that's really the real reason. There are other high altitude balloon opportunities. I think if you're under 4 pounds, the high altitude ballooning club at U of A will fly your instrument under 4 pounds, but we're like 7 or 8 or so. We haven't worked as hard to reduce the weight.
Any questions from people on Zoom?
Vinny, thank you for the invitation. You're there listening.
You are most welcome.
So no question from Zoom? No.
Robert has another question.
I guess I want to ask one last thing. Would your system benefit at all from pre-filtering things, like pre-filtering out light in the visible, like for that first one when we sent up into the clouds? Would it?
I don't think my detector has any sensitivity in visible. That uncooled microbolometer.
Okay.